Today we're going to look at solving compound inequalities. Now you've seen inequalities before, x is greater than 2, y is less than or equal to 1, those types of things. But we need to start putting these together and learn how these are going to interact with each other. And eventually we're actually going to use this idea to solve some inequalities that have absolute value statements in them. So before we keep going, let's make sure we know, how can we graph a compound inequality and what makes it compound? So that word might sound a little familiar to you. When we were studying geometry logic, we had compound statements. So we had our and statements and our or statements, and they were compound because they were made of two ideas that we put together. Well, it's the same thing for compound inequalities. We have two inequalities that we need to figure out how they interact with each other. And just like in logic where we had and or statements, it's the same thing with inequalities. So we're going to have some inequalities that actually have that word and, or it's implied in how it's written. And the same or similar to when we did logic, when we had the and statements, both pieces had to be true. Well, this is where we're talking about both constraints having true information. In other words, where they overlap. So you might want to write that note in there. We're going to overlap. And then we also have our or statements, again, just like in logic. But these are where we're actually going to have two separate sections. So it can either be in one section or the other section, but it's not going to be in both places. So we can think of those as no overlap. And then we're going to look at scenarios where we might have one or the other, but we're hopefully going to be able to tell the difference between the two with some examples today. Okay, so first off, how would we even graph a compound inequality? So our example one, we're going to graph the solution set of x is less than 2 and x is greater than or equal to 1. So I know this is an and because it has the word right in there. So I have a feeling I'm probably going to have some overlap happening, and all I'm going to use is where do those two pieces kind of overlap each other. So if we graph each inequality and then see where they overlap, then that'll be our graph. So we're going to graph x is less than 2. So thinking back to when we were doing interval notation as well, we used this. So less than means we're not actually using 2, but we're getting really, really close to it. So that's when I would put a circle around the 2. And then we're going less than. So all the numbers that are smaller than 2, those are the ones I want to kind of highlight. So I'm going to draw an arrow going to the left. Okay, now graphing x is greater than or equal to 1. Well, if I have the equals piece in there, then that means I'm including the -1. So I'm going to use a filled in circle. And then x is greater than or equal to 1. That means I want everything that's above the -1, all of the greater values. And so what I'm going to do for my final solution set, which is going to be the third graph, is I need to figure out where the intersection between those two graphs are. In other words, where do they overlap? And so I have this 2 point, and I have this -1 point. And all I care about is the stuff that's in between that is actually shaded in on both graphs. So we had the closed circle on -1. We had the open circle at 2. And we're looking at the pieces that are all in between. Now, not just writing this or drawing this on the graph, we can also write our solution set. And the way we do that, again, using or noting I have the word set in there, solution set, automatically I know I'm going to use curly brackets. We're going to write it kind of like domain and range. So our solution set is actually all of the x's that are sandwiched in between -1 and 2. So we have a -1 is less than or equal to, because we included that number, our x, but less than 2 because we didn't include. It was non-inclusive. And that is our solution set for graphing those two inequalities, or the compound and inequality. Okay, let's look at another one. So this one's written out a little differently. So we have -1 is less than x plus 2, which is less than 3. This is another way that you could see these and or compound inequalities. We don't see the word and if we just had that inequality written, but we have two inequalities in there and they're kind of overlapping in the middle where we have that x plus 2. So actually what we want to do, kind of like when we solved our absolute value problems, is we're going to break it up into two pieces. The x plus 2 is going to get repeated, and then we're going to write it once with the inequality on the left, once with the inequality on the right. So we're going to solve out -1 is less than x plus 2, and we're going to do another one that's x plus 2 is less than 3. And that's where we're going to get our two different graphs, two different solution sets that we'll want to see where they overlap. And so in each one of these, all we have to do is move the 2. So we're going to subtract 2 from both sides. So -1 minus 2 is -3. But you're probably more used to seeing the x on the left, and it might be a little easier to interpret things that way. So I'm going to rewrite him as x is greater than -3. I just want to make sure the open piece is going through or going towards the same part, or the pointy end is going towards the same part. Really doesn't matter which one you focus on. But if I flipped my order, I have to flip my signs. Okay, and then our second one, so let me just kind of underline this guy a little. So then in our second one, x plus 2, again, subtract 2 from both sides, we're going to get x is less than 1. And so these are our two inequalities that we're going to graph. So x is greater than -3, x is less than 1. So greater than -3, again, we are not including because we don't have the equals bar in there, but we want everything that's above the -3. Same thing, 1, not included because we don't have the equals bar. Everything below -1. So then looking for where we overlap, we've got the section in the middle where they both have values. We're going from the open circle to the open circle. They were both open. And shading in the middle. So that means our solution set, again, x is sandwiched in between our -3 and our 1. Or I can write it as solution set, but it's actually the same inequality. So -3 less than x less than 1. And again, alligator eats a bigger number. So make sure that's always facing the larger numbers when you're writing these final solution sets. Okay, go ahead and pause the video and try out examples 3 and 4, and then come back to see how you did. Okay. So number 3 has the and written out, so I know I'm going to have two solutions. Left-hand solution, all I have to do is add a 1 to both sides. Right-hand solution, I need to subtract 2. But again, notice, I did not flip my sign. You only flip your sign if you are adding, if you are multiplying or dividing by negative. So here's another trick. I didn't give you 3 graphs to use on this one. So what I like to do is maybe draw one above, one below, and then the answer I can put on the number line. So one is y is less than 3. I've got an open circle going to the left. So then I have y is greater than or equal to 1 or -1, which will be a closed circle greater than 1. So that means my final solution goes from the closed circle to the open circle and everything in between. Okay, in other words, my solution set is going to be everything sandwiched between -1 inclusive and 3. So now let's look at number 4. And in number 4, we don't have two separate inequalities. So we're going to start by writing this out as two separate inequality equations for us to solve. And so on the left-hand side, we have d minus 3 is less than 6d plus 12. And I'm taking that whole middle section. And I'm going to repeat that for the second one. So 6d plus 12 less than 2d plus 32. So let's go and solve each one individually and see what that gives us in terms of a solution. So on the left-hand equation, let's go ahead and subtract d from both sides. So that'll keep our d expression positive. So we can have a -3 less than 5d plus 12. Then we can subtract 12 from both sides. So -15 less than 5d. And then we can divide both sides by 5. And again, I'm dividing by a positive number, so I don't need to worry about changing the inequality. So we'll have -3 is less than d. Now, usually when we're looking at our inequality, we think of having the variable on the right-hand side, excuse me, the left-hand side, not the right-hand side that we have now. And that can help when we're drawing out our solutions on the number line. So let's go ahead and flip that around. And we just need to make sure that we have the inequality going the same way. So we have the open section opening up to the D, and then we have a -3 on the other side. Again, double check, pointed end goes towards that -3. Now, in our second inequality, again, move things over to combine your like terms. Let's subtract 2D from both sides. So that would give us 4D plus 12 less than 32. Add 12 to both, excuse me, subtract 12 from both sides. So 4D is less than 20. And divide both sides by 4. So D is less than 5. And so now putting these both on the number line, we have D is greater than -3 because it doesn't have the equals portion. It's going to be an open circle, and that will shade up or to the right. And then we have D is less than 5, so same thing, closed, or excuse me, open circle, shaded to the left, and those two arrows actually overlap in the middle. And so our final solution set would be that our D is sandwiched in between the -3 and the 5. And so those are a couple of and inequalities where we're going to have an overlap between the pieces that we kind of have to shade or draw through on our number line. So our next couple examples are going to be our or inequalities. So these inequalities are going to have two different sections that do not overlap. And we'll have multiple arrows on the same number line. So again, this one, and actually if I scroll down and look at 5, 6, and my extra ones, it's very clear that we have the or in there. So there's not going to be really much difficulty deciding, are these and ors, are they overlaps or are they not? If you see the or, then most likely you'll have no overlap. But again, wait to see what your solutions look like, and then make that decision. Do you think it matches up? So let's try these out. Okay, example number 5. So again, I want to get each variable by itself. In my first equation, I'm going to subtract 1 from both sides, then divide by 2. So A is less than 5. Right-hand side, again, a couple different ways that you could do this. I'm going to go wild and crazy, leave my variable on the left-hand side, and I'm going to subtract a 3A from both sides. So that'll give me a -2A is greater than 2. And then I just have to be careful. I'm dividing out that -2 to get the A by himself. So I just need to make sure that I flip my sign around when I do that. Excuse me. So 2 divided by -2 is just -1. So again, I can look at my overlaps. I put 3 graphs on here so you could check to see how it looks. So let's try this out. So X is less than 5. Again, no inclusive. So open circle. But then we also have A is less than -1. Huh. So wait a second, let's think about that. We have multiple things happening. It could either be in one section or it could be on the other. And we do have some overlap happening, you know, kind of past that -1, but we want to make sure that, you know, it could be in either section. So this is going to look a little strange. I'm going to actually graph this as open circle at the 5 and then everything to the left, not just the intersection. Because that way, if I pick some point, let me change colors. So let's say I pick a point over here, and I pick the point -3. It definitely works on that first inequality. It works on the A is less than 5. But it doesn't work on our second inequality, A is less than -1. So as long as it works on one or the other, we can include it in our solution set. So again, at a +2, again, we would want to include that in the solution set because it's one of the graphs or the other. If we pick something like -4, it just happens to be in both of them. So our solution set on this one is actually going to be A is less than 5. All right, let's try the next one. Okay, so same thing, 2 separate inequalities, 2 separate solvings. Okay, here we go. So 1/2 n is greater than -2, or 2n minus 2 is less than 6 plus n. So again, I'm going to go ahead and clear out my fraction. Let's multiply both sides by a 2. So we're just going to have n is greater than -4. He's done. Okay, on the right-hand side, again, doesn't really matter where you move your n's. I'm going to go ahead and subtract an n from both sides. And then I'll have to add 2 to get that n by itself. So we have our 2 inequalities. So we have n is greater than -4. So I circle -4, and it's everything above. Then I also have n is less than 8. So n is less than 8. Well, wait a second. If this is an or, I don't care just about the overlap. But if I consider, let's see, I could use a +8, +9. Everything out that past this way is still going to be bigger than the -4. And everything out past this way, like a -9 or -10 or what have you, is going to work for our second inequality. So we need all the info that works for either the first one or the second one. So actually, we could highlight, or we could draw in the entire graph. And so if we're hitting every single number, well, that means that our solution set is actually all reals. So n is in the set of all reals. So again, if you're worried about, hey, am I actually figuring out something that works? To check your answers, again, pick a random point, plug it into your equations. If we have an or statement, then as long as it works in one or the other, it is a possible solution. So let's actually test that out. So I'm going to go ahead and pick 10. And so let's plug that in. I'm going to change my color. Okay, so let's plug 10 in to see what works. Again, as long as it works in one or the other, it is a possible solution. Okay, so original equation would be 1/2 times 10 is greater than -2. Okay, so that gives me 1/2 is 5, and 5 is definitely greater than -2. So as soon as I have one solution that works, okay, I have a valid solution. It checks. Again, it's just like the and or statements in geometry from last year. For and statements, both pieces have to be true. You need your overlap. But for or statements, as long as one piece is true or the other piece is true, you can include that in your solution set. Okay, just like before, go ahead and try the you try problems, pause your video, and then come back to see how you did. Okay, real quick, let's go through our last set. I need to switch this down just a little bit. Okay, both of these are or statements. So I have a 2x is going to be less than or equal to 2, subtracting that 4. So x is less than or equal to 1. Second one, I'm going to go ahead and move my 2x, so subtract 2x from both sides. So -x is greater than or equal to -4. But to get rid of that negative, I need to divide both sides by -1, which means flipping my inequality. So x is less than or equal to +4. Well, wait a second. X is less than or equal to 1, and x is less than or equal to 4. So we have a 1 less than. We have a 4 less than. We want to include every possible thing. So the x is less than or equal to 1 is actually included in x is less than or equal to 4. So our solution set is really just x is less than or equal to 4. Okay, number 8. So 3a plus 2 greater than or equal to 5. Let's subtract our 3 first. Excuse me, subtract our 2, which gives us a 3. And then divide both sides by 3. So a is greater than or equal to 1. Sorry about that. That is an a. So then 7 plus 3a is less than 2a plus 6. I'm going to go ahead and subtract a 2a from both sides, which will give me 7 plus a less than 6. Subtracted 7 from both sides. Again, do not change your sign unless you're multiplying or dividing by the negative. So we get a is less than negative 1. Okay, so a is greater than or equal to 1. Filled in circle, everything above. A is less than negative 1. Does not include the negative 1. Everything lower. We finally have one of these where we don't have any overlap. So our solution set, we just have to mention both things. So we're just going to say that a is greater than or equal to 1, or a is less than negative 1. As always, let me know if you have any questions. Pop back into Zoom if you have, especially if you run into any difficulties on our practice for today.